All right. So thank you to the organizers and IPAM for organizing this event. It's really, I think, long overdue to get the C-star classification folks and tensor category folks, subfactor people in the same room. I guess we're not really in the same room, but it's at least a good try. Okay. So yes. So as you may notice, the title of my talk is slightly different than what I put on the website, but the abstract is the same. I just kind of changed the titles. And so, wait a second. Click. Okay, so what is the theme? There are many themes of this conference, classification, this sort of thing, but one kind of thing that we would like to get across is that fusion categories can act on C-star algebras. And this is motivated by the well-studied special case of cocycle actions of finite groups. And so what this talk is about how to build examples that are just beyond this kind of usual group action framework, not too far beyond, just slightly beyond, and they still use groups and stuff, but an extra piece of data called an anomaly kind of comes into play. And this terminology is inspired by physics, and I kind of co-opted it from physicists because I think physicists have more of a knack for naming things than mathematicians do, and anomaly sounds better. And indeed, in physics, this would be called an anomaly. So that's where this word comes from. It's very closely related to what Sam was talking about yesterday about lifting obstructions and this sort of thing. Not exactly the same thing, and I'll get to that in a little bit. So another thing that's a bit orthogonal to the sort of thing Sam was talking about yesterday is that I'm very interested in C-star algebras, not necessarily, I mean, of course, classifiable C-star algebras are awesome because you can classify them, but also C-star algebras that are related to geometry and topology kind of naturally occur in physics. And I'm talking about both high energy and condensed matter physics. So in particular, in classical field theory, you have the algebra of sections of vector bundles and of endomorphisms of vector bundles, these sort of things. And in topological insulators, which is a branch of condensed matter physics, also row C-star algebras appear, and T-duality and string theory uses a lot of these kind of geometric and topological C-star algebras, which are usually very much non-simple. And so they kind of fall pretty far outside of the spectrum of classifiable C-star algebras, as far as I understand. And so finally, before I get started in the technicalities, I want to mention that this whole thing is inspired by Vaughn's thesis. When I was a grad student, Vaughn gave a course, and he tried to explain some of the stuff in his thesis, and I didn't understand it at the time. And over the years, people keep telling me, "Oh yeah, that results in Vaughn's thesis. That's in Vaughn's thesis." And so, this summer, I decided it was finally time to read Vaughn's thesis. And I realized all of these ideas people have been telling me about, you can use it to answer some questions I've been thinking about this anomalous actions for these kind of geometric C-star algebras. So this is very much inspired by Vaughn's thesis, and I would like to thank him. This whole thing is indebted. Okay, so let me tell you, people have been throwing around the word cocycles a lot during this conference. So let me just tell you give you an actual definition. What is a 3 cocycle? So if you have a discrete group, then a unitary 3 cocycle is just a function that takes in, 3 G cross G cross G to U1, and it just satisfies this equation. Okay, it's just a solution to this equation in this for this function. And if you take the set of all solutions, this forms an abelian group under just pointwise multiplication. This technical term is called, the cocycle is called normalized if it takes the value 1, if any of those GHK arguments are the identity. And you can always kind of assume things are normalized without loss of generality. You can make that precise in the context you want to, but that's just an abstract nonsense sort of thing. And then there's this notion of a co-boundary. So a function from G cross G to U1 is a co-boundary if omega is the co-boundary if there's some other function from G cross G to U1 that's related to omega in this way. And you should think of the omega that arise from these functions as trivial. These are the trivial 3 cocycles. And this C is a trivialization of the 3 cocycle. Okay, it's a witness to the fact that omega is trivial. And if you take all the three cocycles and you mod out by the co-boundaries, you get a group called H3 of G, which is the cohomology group. Okay, so that's kind of the basic setup. That's what we're working with. So here's the definition. Instead of describing this as a tensor functor, or if you look at my paper, there's all this stuff about two groups. But I'm just going to give you a very kind of super concrete down-to-earth definition. So if you have a group and you have a three cocycle, then an omega anomalous action of G on the C-star algebra B is just an assignment for each group element. I have an autoequivalence, an automorphism of B. And then I have a family of unitaries in the multiplier algebra satisfying these two equations. So first, these unitaries should intertwine the composition of the two automorphisms and the automorphism corresponding to the product of the group elements. And then they should satisfy this kind of cocycle equation. If I make omega completely trivial, this just reduces to the definition of a cocycle action that Stefan was talking about in his talk. So what this is it's a deviation of a cocycle action, and that deviation is controlled by the scalar function on G that satisfies these cocycle equations. Okay, so it's just slightly beyond the usual notion of a cocycle action. It's cocycle action up to this three cocycle omega, up to this other cocycle. Okay. And for finite, so you've been, I was hoping we had a more in-depth discussion about Hilb G omega by this time, but Hilb G omega is a fusion category whose associator is twisted by a three cocycle. And for finite G, an anomalous action of G, as I've defined above, is actually the same thing as an action of the fusion category Hilb G omega, with the extra stipulation that each group element should be acting by an automorphic bimodule, or should be acting by one of these twisted bimodules that Dave was just talking about in the discussion section, and I believe Sam talked about yesterday. So it's not completely general here. Like there could be Hilb G omega actions that aren't from anomalous symmetries, but certainly anomalous actions give you Hilb G omega actions on the C-star algebra. Okay, and then to discuss the relation with the lifting obstruction that Sam was talking about. So if the multiplier algebra B has trivial center, then this is basically exactly, it just reduces to what Sam was talking about. Namely, this thing corresponds to a G kernel, which is a homomorphism from G into the outer automorphisms. And then, he described how you get a three cocycle out of that. That three cocycle has to agree with this omega that we're talking about here. Now, if the multiplier algebra does not have trivial center, and actually all the things that we're interested in this talk are very much going to have non-trivial centers, then these are not, the lifting obstruction and this scalar three cocycle aren't the same thing. They have to be compatible in a certain way, but they're not like equalities. And understanding their relationship is kind of the heart of trying to find anomalous actions. Great. So some examples that are just kind of already known sitting around. So I wanted to mention Vaughn's, the results from Vaughn's thesis for every finite, we've seen this several times, but for every finite group G and every anomaly, so an anomaly is just a three cocycle on the group, there exists, and I wrote essentially unique because I don't want to get into the weeds, but it's basically, cocycle conjugacy. But there exists an essentially unique omega anomalous G action on the hyperfinite 2-1 factor. There are also, I should mention, from general subfactor theory, it's known that every fusion category emits actions on for example, Popov-Shatenko showed that they emit actions on the free group, LF infinity, and these sort of things. So there are other things that are known, especially in terms of existence in the setting of 2-1 factors. For the C-star algebra situation, so there are some kind of general constructions of fusion categories that in particular give these anomalous actions if you restrict to Hilb G omega. Particularly if you, on AF algebras, if you just run the subfactor construction and you just take, as Sam said, you replace everywhere all the weak closures with norm closures and make sure everything works. And indeed, it does for AF algebras. Kunz-Krieger algebras, this is a construction that was studied by Izumi, who showed that fusion categories emit nice actions on Kunz-Krieger algebras. And more recently, Roberto Hernandez Palomares and Mike Hartglass showed, fusion categories admit actions on free graph algebras. And so there are these general ways to take a fusion category and find some C-star algebra that it will act on. Okay. But the problem with all of those constructions, all these kind of subfactory constructions, is they produce only a very special set of algebras that you can be acting on, namely AF algebras, Kunz-Krieger algebras, free graph algebras. These algebras all have kind of a combinatorial feel, and they're kind of a little bit removed from the kind of topological C-star algebras I care about, like continuous functions on a smooth manifold or something. Okay. But so anyway, another easy example is if you just think of G as a discrete set. Then if I take the continuous functions on G just as a commutative C-star algebra, then then the group with any anomaly will emit an action on that thing. So you can always find anomalous actions of G, kind of think of this as acting on itself or something like that. This is like a regular action, but it ends up acting on these things. Okay, so here's just some general examples. But yeah, as I was somewhat complaining about, the topologies, the C-star algebras that appear in a lot of physical applications are related to topology and geometry. So things that I would be more interested in seeing anomalous symmetries of are things like C of M tensor K. So here I want M to be something like a smooth connected manifold, like a sphere or a torus or something, very, nice. And maybe a stabilization of that, because often you care about a vector bundle over that space and take sections of the sections of the endomorphism bundle. You want that algebra to be under consideration for things like classical field theory. So, to throw all those things together, let's just stabilize the whole thing. Take C of M tensor K. That would be an awesome C-star algebra to study in terms of these kind of anomalous symmetries. And another example that has appeared more recently in the theory of topological insulators are the row C-star algebras for bounded geometry metric spaces. And these are, of course, are very closely related to the large-scale geometry of the metric space. And so, I'm kind of putting it in the same class as the commutative C-star algebras and saying that it's geometric or topological instead of being kind of combinatorial like the other sorts of algebras for which we know how to build. Okay, and another thing is that in some of these situations, the anomaly, this 3 cocycle that I'm talking about, actually has physical significance, particularly in symmetry protected topological insulators and this sort of thing. The anomaly really means something to physicists, and so we would like to understand: can you even have these anomalous symmetries in these situations relevant? And so it kind of motivates this question that got me thinking about a little while ago, how common are anomalous actions in this kind of geometric or topological setting? Do they even exist at all? Like if I make M nice and connected, and there's not a lot of projections running around in M, like can I even find any of these actions? And some difficulty. So the first thing to note is that if omega is non-trivial, then there are no trivial actions. There just isn't a trivial action. I can't act on a point. So that means I can't even find trivial actions of this thing on a C-star algebra. For a normal group, there always exists an action on a C-star algebra, right? I can always take the trivial action. But as soon as that 3 cocycles in there, if it's non-trivial, there are no trivial actions. So I'm not asking, are there any interesting actions on these things? I'm asking, are there any actions at all? Because there's not a trivial action. So if you find an action, it kind of has to be, in some sense, non-trivial in some sense. And yeah, as I mentioned before, the usual subfactory type constructions produce these combinatorial these C-star algebras coming from kind of combinatorial type constructions. And these things tend to have lots of projections running around. And you can kind of see how to make, when you get into the weeds, once you have lots of projections, it's not so hard to get anomalous actions. But if I start throwing out projections, it's much more difficult to try to actually build anomalous actions on the C-star algebra by hand. Okay, so that's kind of a little roadblock to using the tools that I personally was already familiar with about how to build fusion category actions and stuff. And then one thing that I kind of came to realize when I was studying this stuff is that, especially if you're looking at the case of symmetries, anomalous symmetries on topological spaces, if you have line bundles, that actually makes things really interesting, because line bundles give you nice examples of bimodules over C of X that are invertible. So, your group element could be sent to that, but they're not twisted by an autoequivalence. So they're really kind of interesting things, and they give you interesting automorphisms of the stabilization, right? Line bundles give you automorphisms of the stabilization that don't come from just an ordinary homeomorphism on the space, like the other kind. So that actually it allows for interesting things to happen, okay? And that's what makes this sort of stuff work. So I'll start by just giving you some theorems about anomalies and how they appear in regards to topology. So the first is a no-go theorem. So let X be a compact, connected, locally path-connected Hausdorff space. So if H1 of X is 0, then you can't find any anomalous actions of any group with any non-trivial omega on the C-star algebra C of X. And H1 here means singular cohomology of the space. Okay. If, in addition, X has no non-trivial complex line bundles, and if it's a nice space, like if it's homotopy equivalent to a CW complex, then this is the same thing as asking for H2 to be 0. So, for example, things like homology spheres of large dimension. Then with this extra assumption, then there's no anomalous actions on even the stabilization. So even if I afford myself the non-commutativity of having compact operators, that gives me more projections to work with because now I'm allowed to use all the projections coming from non-trivial vector bundles. If this H2 is 0, then I still can't find any anomalous actions. So that's kind of like the first roadblock that you come to. Okay, no, there's a no-go theorem. And for a while, I thought that this no-go theorem might be pretty this hypothesis that H1X being 0, I thought, might not be required. And I thought actually there might be a general no-go theorem. But it turns out that's not the case. So following the no-go theorem, we have this go theorem, which says for every finite group and every omega and every n greater than or equal to 3, you can find a closed connected n-manifold and an omega anomalous action of G on the stabilization C of M tensor K. And furthermore, if n is greater than or equal to 4, you can choose M so that this H1 is 0. So that means that the hypothesis of the first bullet point in the no-go theorem are satisfied. And it's telling you that in this n greater than or equal to 4 case, you're really using the non-commutativity afforded by stabilizing. Because I know I can't have an anomalous action on C of M. I can only have it on stabilization. So that's kind of an interesting thing going on there. And I'll sketch, after I talk a little bit more about some other things, I'll give you an idea about how this construction works. The no-go theorem it uses basically standard cohomology and standard algebraic topology. And when I say standard, I mean it's fairly elementary. There's no like super high powered theorems. It's just, algebraic topology plus cohomology theory. You can kind of come to this no-go theorem pretty quickly. Okay. So before I kind of give you an idea of this construction for the go theorem, let me just also mention some stuff from course geometry. So a no-go theorem, if you have a discrete metric space with bounded geometry, then actually, no matter what, there's just no anomalous actions of any group on the row algebra C star X. And by the row algebra, I mean, the row algebra, not the uniform row algebra, really the non-unidal row algebra. And the reason why, when you start looking at the row algebra more carefully, is because there's this special, minimal ideal of compact operators. That's the unique minimal ideal. And so any anomalous symmetry on a row algebra would have to restrict to an anomalous symmetry on the compact operators. And you can't have that because the compact operators are too simple. So that's kind of where this no-go theorem comes from. It's not super deep. It's just the fact that the compact operators are the unique minimal ideal in any row algebra. But so that might lead you to say, okay, well, what if we quotient out by that minimal ideal of compact operators? Then we're led to these C-star algebras, which have been called the row corona. They're not the corona of the row C-star algebra, but they're called row coronas by some authors. I forget who off the top of my head, but I saw this name in the paper, the row corona, which is C star X mod the compact operators. Once you get rid of those compact operators, then you have the following theorem: for every finite group and every anomaly, there's some discrete metric space with bounded geometry, and it also has property A, and an omega anomalous action of G on that corona, on the quotient of the row algebra by the ideal. So once you get rid of that ideal, you can have all kinds of anomalous actions happen. Okay, so that's just kind of something I mentioned in passing. And this Go theorem actually uses the same construction as the topological thing. So let me kind of get into how that works. So this theorem is, you can trace the ideas back to Eilenberg and MacLane, who have an analogous theorem in just the setting of groups. And then in the late 70s, early 80s, Vaughan Jones and Colin Sutherland kind of had an adaptation of this for von Neumann algebras. And basically what I have here is just an adaptation to the C-star setting. In all of these situations, it's all essentially algebraic. So really the proof is almost the same as the proof in the Eilenberg-MacLane case. You just have to check that the topology works. But yeah, so here's the situation. So here's the setting. So suppose we have a group Q, a 3 and a normalized 3 cocycle omega. Suppose we have a different group G and a surjective homomorphism from G onto Q, and we'll call that kernel K. And then we want a normalized cochain on the big group G that trivializes the inflation of omega up to G. So given this homomorphism from G to Q, I can take omega and pull it back. This is called inflation, and get a 3 cocycle on G. And so what I'm looking for is a trivialization of that pulled back 3 cocycle on the big group G. And then finally, now suppose I have an ordinary action of that big group G on the C-star algebra B. Then the theorem is that you can build an omega anomalous action of that group you started with Q on this twisted cross product B cross K, where this is twisted by the 2 cocycle C that you get from restricting this trivialization C to the kernel. Now, this trivialization C is just a cochain, but when you restrict it to the kernel, it becomes a cocycle, a 2 cocycle, because the inflated cocycle restricted to K, the kernel, is just going to be identically 1. So saying that DC equals 1 on the kernel means that it's a 2 cocycle. So this trivialization becomes a 2 cocycle on K, and so I can take this twisted cross product with K, and yeah, you can build an omega anomalous action of Q on that. Okay, so that's the basic idea. So that's great. But there's kind of a problem with that, is that we know, we have a good understanding about what happens for in terms of, if I have a group acting on a space and I take its ordinary cross product, if your action was nice and free or something like that, then that cross product will be Morita equivalent to the continuous functions of the orbit space, right? But when I take a twisted cross product by a 2 cocycle, the thing I get might not be Morita equivalent to the continuous functions on the orbit space. It might be some continuous trace C-star algebra over that spectrum, but it might have a non-trivial Dixmier-Dowdy invariant, right? And so I can't kind of use this construction to build actions on stabilized commutative C-star algebras unless I could somehow guarantee that 2 cocycle, I could actually make it trivial or something like that. So that gives us this following just abstract cohomology lemma. And so this is an extension of something found in Vaughan's thesis. So basically it says, if you have a finite group and a 3 cocycle, you can go find another finite group which surjects onto Q, and so that the inflation can be trivialized, but it can be trivialized by something that restricts to a trivial 2 cocycle on the kernel. So if you remove this restriction to being a trivial 2 cocycle on the kernel, that was just in Vaughan's thesis, but it's just pretty standard dimension shifting cohomology stuff that goes back to the early days of cohomology theory. But getting this thing restricting to the kernel being 1, you have to kind of dig into the construction and make a bunch more careful choices and make your choices right so that you can find a trivialization that does this. But yeah, so that's kind of the main technical thing. And once you have that, now you can use these 2 theorems together to get the thing that you want. So here's kind of the recipe. So suppose I want to find an omega anomalous action of Q on some stabilized commutative C-star algebra where M is like a really nice connected manifold or something. So step 1 is to use the G from the previous theorem, right? and find a free G action on a compact connected manifold n tilde. This is some, so you can just use standard algebraic topology to find such a thing. It's not super hard to do. Okay. Then you can use this above a lemma to obtain an anomalous Q action on the cross product C of m tilde cross whatever that kernel was. We just called it kernel. And this is where, as I said before, you need it to be an untwisted cross product. Otherwise, you'll get some non-trivial Dixmay-Dowdy invariant here, possibly. So you really want it to be untwisted. And then it follows from a result of Philip Green that cross product, the stabilization is isomorphic to the stabilization of the continuous functions on the orbit space under the kernel action. And so that gives you an omega anomalous omega anomalous action on the stabilization. And for the rho C-star algebra, the rho corona result, it's basically the same thing. You just use this kind of cross product lemma that you have, and then there's a theorem about taking the cross product of rho coronas is isomorphic to the rho corona of the quotient, where you take the quotient metric space of the group action on the core space. Okay, and so that's all I have. So I'll go ahead and stop there a couple minutes early. Thank you.